Hi there. Welcome to week 12 for Chem 110. This is some important information about exam 2. As many of you know, especially with all the changes in response to COVID-19, there are just some adjustments that we need to make in order to be flexible. So I've sent you an email and there's some additional information there, but here's the short summary. I think that to be fair to all students, what we're going to do is extend a 10-hour time block that you can sign up for. Anytime during that 10-hour time block, you can set aside 2 hours to take your exam. Part of the reason why we're doing that is because we feel like a window of time is more fair for you so that you can be adaptive to your individual or family needs. And we know that you have many responsibilities ranging from whether you're caring for family and friends to your work responsibilities and your schedule. And so this will allow you some flexibility to adjust your plans as needed, but still protect the time to be able to take that exam and be in a quiet space where you can focus. Some of you have asked why there's a 2-hour time limit on the exam. So this is what would exist if you were taking this exam in class. And the purpose of this exam is to be able to evaluate what you know and how well you know it. And so in order to have time to give you feedback and for that to be as real and as authentic as possible, I want you to try and complete your exams within that 2-hour time block. That allows you to be attentive to all your responsibilities, and it also gives you an accurate representation of what you currently know in Chem 110. So what can you use? Well, I highly recommend that you put together a one-page summary of your notes or resources as a go-to place to start. You can have an equation sheet that's available to you either from what I passed out in class or it's available by email. So there should be no need to memorize equations. And remember, the goal is to see how you think. So I always recommend you have accessible a calculator. There are online calculators if that would be better for you if you don't have one in person. And then you can, of course, have an array of colored pencils or pens or highlighters. So you're welcome to use your whiteboard, essentially any of the tools that would be helpful to you as you take this exam. And then a couple of you have asked, are there still retakes? And the answer is yes, there are. We practice iteration so you can improve your learning. But remember, the exam scores are always averaged. So if you want the best possible score, make sure that you give your best possible response as you're engaging in at least the first pass of exam 1, or exam 2, sorry. All right, so when we think about the norms that we've adopted, we create safe spaces. So the reason we're sheltering in place for COVID-19 is because we want people to be safe. And right, just like any other time, everyone's learning. So questions are always welcome. That's truly the best way that we learn. Knowing that you can rely on others and collaborate is key. So there are tools like Zoom or Google Meets or Hangouts or even a cell phone that sometimes can be really great resources as you're trying to problem solve. This is what scientists do all around the world as they're trying to come up with solutions for the COVID-19 virus. And then iterating, taking a risk and trying again. If it doesn't work the first time, that's okay. We really want you to take what you know and then apply that knowledge to your next attempt. And then probably one of the pieces that I think you will see develop over time is this idea of ownership or agency. Our goal in Chem 110 is to institute strategies that hopefully you will personally adopt and choose to use on your own, even if it's not something that's required of you in a class, because it supports your learning and your own success. Okay, so the purpose of today is really to do a quick recap and review of chapter 9, chapter 5, and chapter 6. This is the new content. So if you recall, exam 1 covered chapters 1 through 4. Chapters 9, 5, and 6 are the new material that we've covered since then. So as we start with our review of chapter 9, what does STP mean? Take a moment, think about what those 3 letters represent, and record in your notes what STP means. This is something that you should always be able to remember. So the S stands for standard, the T stands for temperature, and the P stands for pressure. So temperature is going to be 0 degrees Celsius or 273 Kelvin. Pressure is 1 atmosphere or 760 millimeters of mercury or 760 torr. Of note, one of the other conversion factors that we use is that 1 mole of any gas occupies 22.4 liters. So then let's think about what we understand. If we have 2 liters of a gas and that's collected at 25 degrees Celsius and 745 millimeters mercury, what is that volume at standard temperature and pressure? Think about how you would set up this problem. What are the givens? What are the equations that you have access to that would allow you to solve this problem? So if we think about our givens, our P1 would be 745 millimeters mercury. I know that that's pressure because millimeters mercury is a unit for pressure. Liters is a unit for volume, that would be V1, and T1 is 298 Kelvin, because remember, we always convert from degrees Celsius to Kelvin. But what about our P2, V2, and T2? Well, these are our standard temperature and pressure. So our standard temperature is going to be 0 degrees Celsius, which is 273 degrees Kelvin, and 1 atmosphere, or 760 millimeters of mercury. So in this case, we're going to do our conversion or not. It doesn't really matter because the units are going to cancel. So either you convert to atmospheres and the units cancel, or you leave it as millimeters mercury and the units cancel. It's the same either way. And then we're going to rearrange our changing conditions gas law to solve for V2. Once we do that, we can substitute and solve. The most important components that we need to be thinking about are significant figures. In this case, we have 3, and the correct units. In this case, because it's volume, our unit should be liters. Okay, now let's take that understanding of the ideal gas laws and apply it to a different context or situation. So the pressure of an 8.4 liter nitrogen gas in a flexible container is decreased to 1/2 its original pressure, and its absolute temperature is increased to double the original temperature. What is the new volume? So this is an example where we have to really think about how to write out what we know. So take a moment, list the givens that are provided in the problem, and the equation that you would use to solve this type of problem. So if we think about this, our initial pressure, we really don't know. That's not information that's provided in the problem, but that's okay. We'll just call it P1 for now. Our initial volume is given, and our initial temperature, we have the same dilemma. We don't actually know what that temperature is. What about P2? Well, in the problem, we're given the information that it is 1/2 the value of P1. So we're going to say P1 divided by 2. What about V2? Well, that's what we're being asked to solve for. And what about T2? Well, we're told that T2 is 2 times or double the value of T1. Now, if we think about our expression P1 V1 over NT1 and P2 V2 over NT2, we can rearrange that to solve, assuming that we have the same number of moles, so those cancel, for our V2. Now we're going to substitute in everything we have, and you're going to notice that the P1s cancel and the T1s cancel, which leaves us just with numbers. So 4 times 8.40, because remember, we have the 2 in the numerator and we have 1/2 in the denominator, which is the same thing as multiplying by 2. We have 3 significant figures and our units are liters. Again, the assigned values for the pressure decrease by 1/2 and the assigned values for temperature double, and we can represent that using variables. This is another example of how sometimes we can solve a problem even if we don't have enough information. So let's think about then our review of chapter 5. So it's important that you have an understanding of what Hess's law is, because there's not really an equation to write per se. So it's important that you have an understanding of what a state function really means. So here are 2 representations of Hess's law. The enthalpy of a given chemical reaction is constant regardless of the reaction happening in one step or many steps. And if a chemical equation can be written as the sum of several other chemical equations, then the enthalpy change of the first chemical equation equals the sum of the enthalpy changes of the other chemical equations. So that was pretty wordy. Can you say it more simply, or can you say it better in your own words? Here's the way I think about it. The energy change in an overall reaction is equal to the sum of the energy changes in the individual reactions that make it up. So another way of saying this is the beginning and the end are the only pieces that matter. The steps that we take in the middle to get there don't matter. And so our Hess's law can be the sum of everything as long as our final outcome is the equation that we desire. So let's put that into action. Let's use the following data to determine the enthalpy, or the delta H, of the reaction for NO2 reacting with hydrogen gas. That's going to form water and ammonia. So we're going to use the following 2 equations. 2 ammonia goes to N2 plus H2, and nitrogen gas plus water goes to NO2 plus 2H2. So in one case, we have a decomposition reaction. That's the ammonia going to the N2 plus H2. And in the other reaction, we have a synthesis reaction where the N2 is reacting with the water to form nitric oxide. Both of those have positive delta H values. So think about how you could combine or rearrange those equations in order to get to the desired equation, which is the first equation that we looked at. NO2 plus 7 halves H2 goes to 2H2O plus NH3. So if we think about that, then we're going to flip our first equation, because in this case, the ammonia needs to be on the right-hand side of the equation. It needs to be one of our products. And we're also going to divide it by 2, because right now we have 2 ammonias and we only need 1. So that's the same thing as multiplying it by 1/2. When we do that, we're going to have 1/2 N2 plus 3 halves H2 goes to 1 NH3. Then the other thing we need to do is flip the second equation, because our nitric oxide needs to be on the left-hand side of the equation. Oh, sorry, our nitrogen oxide needs to be on the left-hand side of the equation. So nitrogen oxide plus hydrogen goes to nitrogen gas plus water. So you're going to notice that we have 2 sign changes now. So our delta H that was plus 92 becomes negative 92, and we have to divide it by half, so it becomes negative 46 kilojoules. And our other delta H becomes negative 170 kilojoules. When we combine these 2 equations together and we cancel our like terms, we have NO2 plus 7 halves H2 goes to 2H2O plus ammonia. When we combine our negative 46 and our negative 170, that gives us overall negative 216 kilojoules. And if we think about this, technically it should be 220, because we have 2 sig figs, so 220 kilojoules. Okay, let's apply what we know. When 1 mole of sulfur burns an oxygen to form SO2, 1,300 calories are released. When 1 mole of sulfur burns an oxygen to form SO3, 3,600 calories are released. What is the delta H when 1 mole of SO2 is burned to form SO3? So take a moment, think about what you know. You're going to need to write balanced equations for each of these. You should have 3 balanced equations total. And remember that calories or kilocalories and joules are all measures of enthalpy. Right? Enthalpy is typically measured in kilojoules, right? Or kilojoules per mole. So here we go. We have our sulfur plus our O2 goes to SO2. The delta H associated with that reaction is negative 1,300 calories, or negative 1.3 kilocalories. Sulfur plus 3 halves O2 goes to SO3. The delta H for that is negative 3,600 calories, or negative 3.6 kcals. We need the following reaction. SO2 plus 1/2 O2 goes to SO3. And we don't know what the delta H is. So how are we going to get there? Well, the first thing we're going to do is flip this first equation. We're going to flip that equation so it becomes SO2 goes to S plus O2. Remember, 1 O2 is the same thing as 2 over 2. And our delta H is positive 1.3 kilocalories, because it was negative, so we changed the sign. Second equation we're going to leave as it is. Now we're going to add these 2 together. Notice when you're dealing with halves, this is really just like dealing with what's in the numerator. So in this case, it's 3 minus 2, or 1. So I have 1/2, which is what I want. It's my desired outcome. So sulfur plus 1/2 O2 goes to SO3. The delta H for that is negative 3.6 kilocalories. So when I add those 2 together, I'm going to get negative 2.3 kcals, or negative 2,300 calories. Remember, the delta H when 1 mole of SO2 is burned to form SO3 is negative 2.3 kilocalories. To solve this problem, we first wrote out the chemical equations of the individual reactions. Then we rearranged them so that when combined, they resulted in the desired product. We then added in the enthalpies. All right, let's look at another type of problem that we've been solving when we studied thermochemistry. We looked at the difference between heat capacity and specific heat capacity. So think about both the definition and the units associated with each of those concepts. Remember that heat capacity is the heat required to raise the temperature of a substance by 1 degree Celsius. That's measured in joules per degree Celsius. Specific heat capacity is the heat required to raise the temperature of a unit mass by 1 degree Celsius, or joules per gram degree Celsius. Notice this has 2 units that make up the derived unit, whereas this has 3 units that make up the derived unit. We'll see that reflected in the equations for both heat capacity and specific heat capacity. So let's put our new knowledge into action. So a piece of metal weighing 59.047 grams was heated to 100 degrees Celsius and then put into 100 milliliters of water, initially at 23.7 degrees Celsius. The metal and water were then allowed to come to an equilibrium temperature determined to be 27.8 degrees Celsius. Assuming no heat was lost to the environment, calculate the specific heat of the metal. In this case, we first want to make sure that we assign each of our variables so we can distinguish between the metal and the water. We're going to list out our givens based on whether or not it's metal or water. Then we're going to think about what equations are best suited to solving this type of problem. So in this case, this is a heat transfer reaction where the metal is giving off heat and it's giving that heat to the water. So in this case, the mass of the metal is 59.047 grams. That's given in the problem. Our change in temperature of the metal is 27.8, the final temperature at equilibrium, minus 100 degrees Celsius, or negative 72.2 degrees Celsius. The mass of the water is 100 grams. The reason we know that is because the density of water is always 1 gram per milliliter. So if I have 100 milliliters, then I have 100 grams of my water. The change in temperature for the water is 27.8 degrees Celsius minus 23.7 degrees Celsius, or positive 4.1 degrees Celsius. Now I'm going to substitute in what I know. Once I plug in all of my values, you're going to notice that your units cancel. My grams cancel, my degrees Celsius cancel, and I'm left with joules. On the left-hand side of the equation, right, I have grams and degrees Celsius. So notice when I rearrange and I isolate to find my specific heat of the metal, the units I get are joules per degree, per gram, per degree Celsius, which is great because that's the desired unit for the specific heat of the metal. That's how I know that my equation is the correct setup and I'm on the right track. Many folks have asked about this negative sign. Again, remember that metal is giving off heat, which is why the negative sign is here. But another way to think about that is that's the negative sign that actually cancels, right? So when two negatives are multiplied together, they become positive, which is why the specific heat in this instance is positive and not negative, which is good because we wouldn't want to see a specific heat that was negative for a metal. All right, for chapter 6, we spent a fair amount of time thinking about electron configurations. And that's a great place to start our understanding of quantum chemistry. But it's not where we're going to finish, because quantum chemistry really looks at periodic trends. And those are going to be applicable in medicine and agriculture, in engineering and material science. There are so many ways that you're going to be using the periodic trends as you move forward, regardless of what it is you're going to study, whether that's marine science or environmental science or biology or physics. There are so many ways in which you can use these periodic trends. So let's take a look at an example of how we can make sense of them based on what we currently know. The diagram shows the first ionization energies for the elements from lithium to neon. Explain each of the following in terms of atomic structure. So in general, there is an increase in the first ionization energy from lithium to neon. Critically, I want you to notice that the lithium has an ionization energy of roughly 500 kilojoules per mole, whereas the neon has an ionization energy of roughly 2,000 kilojoules per mole. So why does that increase exist? Well, let's take a minute and think about what we know about our electron configurations. The electron configuration for lithium is 1s2, 2s1. The electron configuration for neon is 1s2, 2s2, 2p6. So let's think about how that might impact our understanding. Remember, if you're not sure, the first ionization energy is the energy that it takes to remove one electron. So as you move across the period, the number of protons increases. This increases the nuclear charge, or the attraction of the nucleus for electrons. So it makes sense that neon has a greater attraction for its electrons than lithium. So it's going to have a higher ionization energy than lithium would. Let's look at another example though, because there are other reasons for these trends. So this diagram shows the first ionization energies for the elements from lithium to neon. Explain each of the following in terms of atomic structure. The first ionization energy of B is lower than that of Be. So let's think about our electron configurations or orbital diagrams. So boron has an atomic number of 5. Its electron configuration is 1s2, 2s2, 2p1. Compared to beryllium, which has an electron configuration of 1s2, 2s2. Now in this case, beryllium has completely filled orbitals, whereas boron has one partially filled p orbital. Remember, when we draw our orbital diagrams, 1s has the lowest energy, followed by 2s, followed by 2p. So 2p is going to have the highest energy orbital. So the electron that is lost from boron is in the 2p orbital, while the electron lost from beryllium is in the 2s orbital. Since the 2p electron is higher energy, it actually requires less energy to remove it. Good way of thinking about that is, remember, our orbitals are spheres. They're population densities. Say, for example, if we're thinking about the s orbitals, which means that electrons can be anywhere on the outside of that sphere. That population density decreases as you get closer to the nucleus. So one of the really interesting things about this then is something that's farther away from the nucleus is easier to be removed because there's not as much pull of the nucleus on that object. If we take a look at C, this is the first ionization energy of oxygen, is lower than that of nitrogen. This has a slightly different explanation. So the electron lost from the oxygen comes from a filled orbital, while the electron lost from nitrogen comes from a half-filled orbital. If you're not sure about that, go ahead and write out the electron diagrams for oxygen and nitrogen. So 1s2, 2s2, 2p3 is nitrogen, whereas 1s2, 2s2, 2p4 is oxygen. So the electron-electron repulsion in oxygen is what causes that electron to be more easily removed. Last but not least, D. What if we're comparing not across a period, but across a group? So predict how the first ionization energy of sodium compares to those of lithium and of neon. So sodium is below lithium in the alkali metal family. So the electron that is lost is actually in a larger shell, farther from the nucleus, making sodium's first ionization energy lower than that of lithium's. Since lithium's ionization energy is less than neon's ionization energy, we know that sodium's will also be less than neon's. So here's the really cool part about studying periodic trends and understanding electron configurations. You can apply them to make sense of anything from electron affinity to electronegativity to first ionization energies to atomic radius and size. And all of those are great ways to be able to make sense of the world around you. So, as a reminder, there are 4 science practices that you are constantly engaging in and you will definitely be engaging in as you take exam 2. You're going to be asking questions and defining problems. You're going to be analyzing and interpreting data. You're going to be constructing explanations and designing solutions. And you're going to be engaging in argument from evidence. If you can do all of those things well, then you're going to do a great job on exam 2. As a reminder, you're not going to want to miss discussion on Thursday because we're going to be looking at how to draw Lewis structures. We're going to introduce that topic on Wednesday in class, but Thursday during discussion is really when we're going to have a chance to practice and make sense of our new learning. So don't forget, you've got one more important task to do. That's organize your goals. Think about your thinking. We want to make sure that we're incorporating metacognition into our practice. For example, you're going to ask yourself, do I really get this idea? Could I explain it to a friend? Do I need more information or knowledge? or do I need more practice? And then reflect on your learning. What was it that made sense? What might I need refining or reframing? And what are you curious about? Who do you learn well with? And what are your next steps? If you do that, you'll be ready to go for Wednesday's class, and you'll certainly be ready for exam 2. So today we did a review. Wednesday, we're going to be tackling chapter 7. Don't forget to sign up for exam 2, and we'll see you soon. Have a great day.